This video will cover a solution guide to problem 68 from chapter 14. A block with mass m rests on a frictionless surface and is connected to a horizontal spring or force constant K. The other end of the spring is attached to a wall. A second block with mass m rests on top of the first block. The coefficient of static friction between the blocks is given. Find the maximum amplitude of oscillation such that the top block will not slip on the bottom block. There is an equation given for the maximum acceleration of an object in simple harmonic motion. However, I think it would be beneficial to show how to derive the expression so that if you happen to forget it, you can still find a way to the answer. Let's start by drawing free body diagrams for each block and applying Newton's second law to each. We are going to assume the spring is being stretched out of equilibrium, but you could also do this assuming compression. The bottom block is being acted on by the spring. Because the spring is being stretched, it'll try to pull the block back towards the wall. We also have the normal force from the floor pushing the block up, its weight pulling it down, and the normal force from the smaller block on top pushing down on the bottom block. The green block has the force of friction, which in this scenario is opposing the block's positive velocity. It also has its weight pulling it down, and the normal force from the bottom block pushing it up. From these diagrams, we can pull our four Newton law equations in the usual fashion by summing the x and y components of each block and setting it equal to the mass times acceleration. There is only the frictional force acting on the top block, so we find that the force is equal to the mass of the green block times the acceleration of the system in the x direction. Because the acceleration is no longer a constant value and is now dependent on the block's position, we are going to represent acceleration as the second time derivative of the position function. The y direction equation for this block simply tells us that the normal force exerted on it by the bottom block is equal to the weight of the top block. We can now relabel this force on the bottom block diagram. For the bottom block's x direction equation of motion, we have that the force of the spring is equal to the mass of the entire system times the acceleration in the x direction. This is the same acceleration as the top block, so we will represent it in the same way. The y equation for this block doesn't actually tell us much. It simply reaffirms that the apparent weight of the bottom block is equal to the summation of the weight of the top and bottom blocks. All we've done so far is figure out what equations we have available to us to work with. So now let's start working on the problem at hand, which is finding the maximum amplitude of the oscillation that is allowed to keep the top block from slipping around. In other words, we are looking for how far we can displace the spring out of equilibrium before the oscillations that displacement will cause will make the top block slip. Let's start with the equation of motion for the top block in the x direction. The definition for the maximum force of static friction is equal to the coefficient of static friction multiplied by the normal force, which in this case is just the weight of the top block. It's at this point where we need to pause and figure out the equation for the acceleration of our system in order to continue. Another way of writing the second time derivative of the position function is the time derivative of the time derivative of the position equation, which is the amplitude multiplied by the sine of omega t minus phi plus some constant b representing an initial position displacement. Taking the first time derivative of this equation brings a factor of omega out in front, and the sine turns into a cosine function. The second derivative brings out another factor of omega, and the cosine turns back into a sine function. We are just interested in the magnitudes since we already used our diagrams to assign the direction to all our forces and accelerations. So now that we have our expression for the acceleration, we can continue where we left off. Substituting the expression for the acceleration into our equation of motion for the top block in the x direction gives that the coefficient of static friction multiplied by the acceleration due to gravity is equal to the acceleration of our system. We can go ahead and solve for a, but it's clear that we aren't done yet since we don't have the values for omega, t, or phi. With this in mind, let's look at the equation of motion of the bottom block in the x direction. If we sub our expression for the acceleration and the definition of the force from the spring into this and rearrange slightly, we find this expression here. Like I briefly stated earlier, the amplitude of an oscillation is equal to the maximum displacement from a spring's equilibrium position, so x max is equal to a, and they therefore cancel each other out. If we solve this equation for omega squared sine of omega t minus phi, we can substitute its expression into our equation we derive for the maximum amplitude we can achieve. Doing this shows that the maximum amplitude our system can reach without the top block slipping is equal to the coefficient of static friction multiplied by the weight of the total system, all divided by the spring constant of the spring.